Let's look at a quick recap of all the tests we've learned thus far. First, let's look at our known series. We have geometric series, p-series, and telescoping series. Now, geometric, remember, is the sum from n equals 0 to infinity of a times r to the n. Here we look at the absolute value of r. If the absolute value of r is greater than or equal to 1, we diverge. If the absolute value of r is less than 1, we converge. P-series were the sum from n equal 1 to infinity of 1 over n to the p. There, if p is less than or equal to 1, we diverge, and if p is greater than 1, we converge. For our telescoping series, we needed that minus sign in between them, and that just meant that our terms were going to cancel out. So we found the sequence of partial sums, S sub n, and then if the limit of the sequence existed, the series converged. If the limit of the sequence did not exist, the series diverged. Then we looked at the following tests. We had the nth term test, which said if you take the limit as n goes to infinity of a sub n, and you end up with a number that's not 0, then your series diverges. But if you take the limit as n goes to infinity of a sub n and you do get 0, then your test is inconclusive and you need to find a new test to determine if your series converges or diverges. So the nth term test can only tell you if a series diverges. It'll never tell you if a series converges. The integral test? The integral test said that if you can show that your function is positive, continuous, and decreasing for all x's greater than or equal to 1, then you can make the infinite series into an improper integral. Evaluate the improper integral, and if the integral converges, your series also converges. And if the integral diverges, then your series also diverges. The last two are the ones that we learned in this section, the direct comparison test. And for the direct comparison test, if the one that we know converges, then our series converges as long as b sub n is larger. And if our known diverges, then our given diverges as long as our known is smaller. The limit comparison test said to take the limit as n goes to infinity of our given over our known, and if we end up with L, a finite positive number, whatever our known series did, our given series does. So they either both converge or both diverge. Let's do the last three examples where we have to determine the convergence or divergence of the series, and we must identify which test was used. So in these examples, we are not told which test to use. We can use anything that we had on the previous page. If it's a known series, we just handle it as a known series. If not, we have the nth term test, the integral test, the direct comparison test, and the limit comparison test. We get to choose which one of those we want to use and then figure out from there if our series converges or diverges. Let's start with example 8, the sum from n equal 1 to infinity of 3n over 2n plus 1. Well, it does not look like a known series. It doesn't look exactly like a p-series, and it does not look exactly like a geometric series. And there's no minus sign, which makes me think that it's not telescoping. My recommendation is if it's not a known series, the next thing you try is the nth term test. Why? Because if you can take the limit as n goes to infinity of a sub n and get something that's not 0, then you diverge and you're done. It's a very quick test. Unfortunately, most of the time that you try the nth term test, you end up with 0, which means that the test fails. But when it doesn't fail, you get to the answer quickly. So let's try the nth term test here. The nth term test says to take the limit as n goes to infinity of a sub n. 3n over 2n plus 1. Now notice that this is just 3n over 2n because those are my leading terms. If I put them over each other and then reduce, I'm really looking at the limit as n goes to infinity of 3 halves. Well, that equals 3 halves. Well, 3 halves is not 0, therefore by the nth term test, our series diverges. Why does it diverge? Because if you take the limit as n goes to infinity of a sub n and end up with something that is not 0, then you automatically diverge. What about number 9? The sum from n equal 1 to infinity of n over n plus 1 times 2 to the n. It doesn't look exactly like a geometric, and it doesn't look exactly like a p-series. We could try the nth term test here, but if you look at the leading terms, you'd have n over n, and that limit as n goes to infinity would be 1. Then you have a 2 to the n in the denominator, and that would be infinity in the denominator, so 1 over infinity gives you 0, and our test would fail. So instead of using the nth term test, let's use a different test. Typically, I won't use the integral test unless I need to. I prefer the limit comparison test or the direct comparison test. So let's figure out what we could compare this to. We have an n over n times 2 to the n, because this is a leading term, leading term, leading term. Well, the n's cancel here, and that's just really a 1 over 2 to the n, which is a 1/2 to the n. So I'm going to compare it to the sum from n equals 0 to infinity of 1/2 to the n. That is a geometric series. The absolute value of r is equal to a half. A half is a number that is less than 1, therefore we know that this is going to converge. Let's do the limit comparison test. So we're going to look at the limit as n goes to infinity of given, well, this guy here is my given, n over n plus 1 times 2 to the n, divided by my known, or times the reciprocal. Well, the reciprocal of 1 over 2 to the n, if we look at it as 1 divided by 2 to the n, would just be 2 to the n over 1. Notice that our 2 to the n's would cancel. We'd be left with the limit as n goes to infinity of n over n plus 1. Well, that's really just an n over n. And n over n, we know that that's just going to reduce to 1. Well, what's the limit as n goes to infinity of 1? That's 1. Well, 1 is a finite positive number. Since it's a finite positive number, by that limit comparison test, our series will also converge. Last one, number 10, the sum from n equal 1 to infinity of 1 over n minus 1 over n plus 2. Well, this is telescoping. Why do I know it's telescoping? Because of that minus sign. So let's find the sequence of partial sums. Let's find s of n. Well, s of n is going to equal, when I plug in n equal 1, I'd have 1 over 1 minus 1 over 3. Plus, when I plug in n equal 2, I'd have 1 over 2 minus 1 over 4. Plus, n equal 3, I'd have 1 over 3 minus 1 over 5. I'm going to do one more before I go to my n's. N equal 4. I'd have 1 over 4 minus 1 over 6 plus dot 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 plus. If I do n equals n minus 1, I'd have 1 over n minus 1 minus 1 over n minus 1 plus 2 is an n plus 1. Then plus our last one, n equal n. It's 1 over n minus 1 over n plus 2. Now, what cancels? Negative 1/3 and positive 1/3. Negative 1/4 and positive 1/4. If I would have written the n equal 5th term, I know that this guy would cancel. The n equals 6th term, this guy would cancel. So these end up canceling if I would have written the other terms. What about on the other side? Well, I don't really see anything that cancels right now, but think if you would have written the n equals n minus 2nd term, well, that would have been a 1 over n minus 2 minus a 1 over n. So you notice the 1 over n's would cancel. And if you would have written your n equals n minus 3, you would have had a 1 over n minus 3, and then minus, and this would have been 1 over n minus 1, so this one would have canceled. And you know these would have canceled if you would have just written the other ones. So what am I left with? Well, I never got rid of the first term in the first parentheses, or the first term in the second parentheses. So when you're not rid of the first term in the first parentheses, you're always left with the last term in the last parentheses. When you can't get rid of the first term in the second parentheses, you're going to be left with the last term in the second to last parentheses. That is the pattern that it follows when you're finding that sequence of partial sums. If we were to clean this up, S sub n would equal 1 over 1 is just 1 plus a half minus 1 over n plus 1 minus 1 over n plus 2, which is really 3 halves minus 1 over n plus 1 minus 1 over n plus 2. Now we can take the limit as n goes to infinity of this sequence of partial sums. So the limit as n goes to infinity of the sequence of partial sums, 3 over 2 minus 1 over n plus 1 minus 1 over n plus 2 would be 3 halves, and then that's just going to be a minus 0 and a minus another 0, which is equal to 3 halves. Since the limit exists, we know that that means that our series converges. We also know that the sum of the series is going to equal 3 halves because when we find the sequence of partial sums and take its limit as n goes to infinity, that number is always equal to the sum. But this problem did not ask us to find the sum, so we wouldn't have to do that. That's it for comparisons of series.